Good morning, everybody. Got a beautiful winter wonderland going on out there. It's looking gorgeous, but we're inside, and it probably would have been a day when we might have had to have a school delay anyway because the roads are kind of slick. So maybe this is actually a good thing that we're distance learning today. We have worked with GMS Measure, continue to do that throughout basically the chapter, especially whenever we have to apply what we have, which means our word problems. Drawing angles in standard position, we've done a lot of that. We've started to get into some really deep coterminal and reference angles, but we haven't talked about radians yet, and that's what we're going to do today is get more into radians with that. Make conversions from degrees to radians and vice versa. We talked about the formulas for those. Find arc length, going to continue with a little bit of that today. And we're going to make connections between angular and linear motion. My goal is, hopefully, we'll be able to finish up all the notes today. Then tomorrow, you'll just be able to work on all of the homework that we have from section 4.1. So we are down here. Ran out of time talking about that first experience on the track going out in elementary school. And I remember that I was further back than the other people and thinking, well, the teacher just must think that I'm faster, and so she's given them a little bit of a head start here on this. But then as we learn about it, we realize that's called staggering, by the way. They stagger the lanes because as you go around those turns, if you stay in your lane, those outside lanes are actually traveling a little farther. So that's why they're staggered. The running lanes at the Emory Sears track at Bluffton College are 1 meter wide. The inside radius of lane 1 is 33 meters, and the inside radius of lane 2 is 34 meters. How much longer is lane 2 than lane 1 around one turn? And I look at that, and I immediately think, well, those are semicircles. And if I'm going to be talking about semicircles and their arc length, I have to have that in radians. So this is 180 degrees, which would be 1 pi. But I have 2 of these I have to deal with. So I'm going to use a little subscript here to separate those two. We have 2 different lanes, so we have 2 different arc lengths that we're going to look at. But theta for both of those is going to be pi, because we definitely have gone 1 pi. So let's do the outside lane first. That one has a radius of 34 meters, so 34 pi. And then the inside lane will be 33 pi. And we see that the difference between the two is 1 pi meters, which, we'd probably want to know just what is that in terms of meters. And 1 pi to 3 decimal places, rounds to 3.142. So I never did get out there to measure and make sure. I just assumed, like everybody else does, that the measuring was correct on it, and that for each of those there was a difference of 1 pi meters as you go around there. So that's why they stagger them, to make it fair. That definitely talks about how we're using that arc length piece from our objective. Now, this is the piece that I think is really, really helpful. Degrees, everybody understands by this point. But when we get to radians, people find that a little bit harder because you haven't had as much experience with it. So example 10 says, for each of the following angles theta, we're going to find the coterminal angles alpha such that they are the nice ones, the ones we want to work with, which are the positives between 0 and 2 pi. Then find the reference angle beta for each angle. So they're not nice. You look at all of these and they're disasters, quite frankly. But we do these the same way, same kind of steps that we did when we were talking in terms of degrees. But we don't use degrees. So we have to remember that all the way around a circle now, when we're talking in radians, is 2 pi. So I need to know how many full rotations this monster right here, let's see, I want to say it correctly, 149,000,000, oops, I missed a decimal there, 14,998,763 pi, how many times that goes around. So what we're going to do is we're going to divide it by 2 pi to figure that out. Now, whenever you have more than one term in the numerator or the denominator of a fraction, you can use parentheses if you want to punch the whole thing in, or you could look at this and say, well, the pi's are going to cancel out, so I really just need to divide by 2 here. Either way, I think I'll show you the long way, and I better grab my notes here so I can see what the numbers were again. 1,4,998,763 pi divided by 2 pi. And that's what we get, 7499381.5. So that's how many rotations we're talking about here. And what we want to do is take what we had originally and subtract all of those extra rotations, which would be, what do we have here for decimal places? 7,499,381 times 2 pi. 1,499,873 pi minus, then we'd take that, 7,499,381 times 2, and we get 1,499,876.2 pi. And we notice, oh, they're off by 1 pi. This is a 3, this is a 2, the rest of the digits are the same. So what we just found was that terminal ray is going to land at pi. And they asked us to call those coterminal angles alpha. So alpha is pi. Now, the next step is finding that reference angle, beta. And we talked about how drawing is the way we get those reference angles. But this one is a problem, because that coterminal angle lands in exactly the same place that our original angle would be, and that's actually on the x-axis. And reference angles are how far away from the x-axis you are. Well, we're away 0, which really means that we have no reference angle. And that's because we have no reference triangle. Now, you certainly know by now the 2 rules in mathematics. The 2 rules of math are we never give up and there's no crying in math. Those are 2 major rules. So, we of course have a special name for when this happens, when we have angles that land at 0, 90, 180, 270, 360. Those are called quadrantal angles. And we don't have enough background to actually go through and talk any more about those at this point. We will. Eventually, we will talk about those special quadrantal angles. But for now, they just wanted to know, hey, what's that coterminal angle between 0 and 2 pi, and what we would have for a reference angle. B. Oh, I grabbed the blue again. I've got to wait here a minute. There we go. Theta equals Ooh, 36,142.51. Wait a second. There's no label. What does that mean? Somebody unmute and tell us what that means if there's no label there.
It means it's a radian.
It is. And we're used to radians having pi. Well, then how did they get that? Well, they multiplied it out, of course. They had something times pi, and they just went ahead and punched it in the calculator and got it. So we're still going to have to divide by 2 pi to figure out how many full rotations this thing has taken. And I don't think I'll be punching that up on the big simulator. I think I'll just grab my handheld for that. Hopefully you're punching these in along with. All right, so I've got 5,752.259 to 3 decimal places. So now the process is the same as what we did in A. It's just that we're not going to have pi hanging out with us all the time. So this will be 36,142.51 minus 5,752 times 2 pi. 36,142.51 minus 5752 times 2. Which is 11,504 pi. And then we'll go ahead and do the subtraction with the calculator. So 36,142.51 minus parentheses 11,504 times pi. Parentheses and enter. And to 3 decimal places, we have 1.628. So that's our coterminal, alpha. And we've talked about how that reference angle, you have to draw it. We got something weird going on with A here. And we shouldn't be shocked to feel a little bit uncomfortable with this one, since the pi is not in there. But here's what you do. You know it's pi. You also know that they multiplied all of that out and made it numerical. So you think, well, I know pi is 3.142 to 3 decimal places. I wonder where 1.628 would land. Well, if we divide this by 2, we'll have a better idea. So on our calculators, we can punch in pi divided by 2, and we get to 3 decimal places, 1.571. So we realize, initial side, this is going to go a little past that 90 degrees. Like so. Well, how far past that 90 degrees? Because that's what we need. This is a reference angle right here. Well, that's not going to be real hard math either, because we need to know what's pi minus this 1.628. Now, I would prefer to use all the decimals that I had before I rounded to 3 decimal places. So you can either use that second enter key to go back a couple of times or just re-punch it in. So now you've got that full decimal, all to 10 decimal places in your calculator. And then we'll take pi minus that 1.628, blah, blah, blah. And that will give us our beta. .513 to 3 decimal places. So like I said, that one's going to make us feel a little uncomfortable because we don't see pi. But whenever we see that, we should be thinking, oh, so they just multiplied it out. That's all they did. Now, why it makes us uncomfortable? This is not as exact as working with pi. You know, they basically took away the whole reason that we work with radians is to make things exact. But we don't get to choose what the problem comes with. We just have to work with what we're given. And we did that, and we did that successfully. C, thank goodness, pi is back. All right, so we've got 46,365 pi over 7. And we're going to have to divide that whole thing by 2 pi to see what we get. So, you want to make sure you get that fraction in properly. Again, parentheses wouldn't hurt. But we've got our 46,365 pi. And we divide that by 7. And then take that whole answer and divide it by parentheses 2 pi, parentheses. And we get 3311.786. So it's making 3,311 full rotations and then a little bit more. So we have, be careful, I just transposed a couple of numbers there. 46,365 pi over 7 minus 3,311 times 2 pi. And then we'd multiply 3,311 times 2 and get 6622 pi. But we get to this point and we realize, well, now I need fractions. I have to have fractions for both because I need a common denominator here. And of course, our denominator for the second one is a 1. Our least common denominator is going to be 7. So we'll have to multiply our numerator and our denominator by 7. Well, let's see what we get. 6622 times 7 is 46,354 pi over 7. Well, and we take a quick peek and say, well, what's the difference between 46,365 and 46,354? And we realize, well, that's 11. So 11 pi over 7, that's going to be our coterminal angle, which they said label alpha. Now we need to draw it. And this is where our thinking needs to start taking over about radians again. Now these are always written as improper fractions. Notice it's up here as 11 pi over 7. That's an improper fraction. But to draw it, to get that angle on our Cartesian coordinate plane, we want to think of it as a mixed number. So I think of this as 1 4/7 pi so that I can get it drawn properly and figure out what the reference angle is going to be. Because I know where 1 pi is, and then I just have to think, okay, 4/7. Well, that's more than halfway. So I've got to go a little bit into quadrant 4. And with fractions, when you have it as this mixed number, it makes it a lot easier to think, okay, well, what's this space here that I need to go all the way to 2 pi? Well, if you have 1 4/7, it's missing 3/7. So again, we think of it as 3/7 pi, but we write it as 3 pi over 7. Again, doesn't need a label because it's in radians. So whenever we write our answers, they're always going to be as improper fractions, but we think of them as mixed numbers when we want to get that angle drawn on our Cartesian coordinate plane. All right, got another massive one, but this time we have a negative angle. So we know where to start. Got to divide that monster by 2 pi. So again, you want to really carefully punch this in. I'm doing parentheses, negative 789,637 times pi, parentheses, divided by 11, enter, and then divided by parentheses, 2 pi, parentheses. And we get negative 35892.591 to 3 decimal places. But we've done 4 examples. This is the 4th one. This one is negative. So I want you to think about how that's going to change things this time. I'm going to start writing it out. How does that change what we should use to find that coterminal angle? Can somebody please unmute and remind us?
You have to round up.
We do. And we're going to make it positive, first of all, and we're going to round up. Because it's negative, we have to make sure we can get to a positive value. So, 35,893 times 2 pi. Negative 789,637 pi over 11 plus 35,893 times 2, 71,786 pi. But we have the same issue that we had in the last one. We have to go ahead and make a common denominator for these so that we can actually do the addition. And that means you realize you have a 1 and an 11. Least common denominator, going to be 11. We've got more multiplying to do. So 71,786, which should still be in your calculator, take that times 11. So we have negative 789,637 plus 789,646. And again, you do that little bit of math of what's the difference between 37 and 46, and you get 9. And that's our coterminal angle, which we were to label alpha. Now we need our reference. So somebody tell me how we want to think of 9 pi over 11.
As a mixed number.
Which in this case you go, well, how am I going to do that? Well, just separate out the pi. So it'll be 9/11ths pi. And you realize, well, that means I'm not going all the way across, because all the way across would be 11/11ths. I have to go 9/11ths of the way. But doesn't that make it super easy to figure out what the reference would have to be? Can somebody tell me what the reference would be for this one?
2 11.
It would, yeah, because you're too short of being all the way to 11. So again, we think of it in terms of being a mixed number, or separating the pi piece out of there in a mixed number. And when we write them, we definitely write them as improper fractions. That has been historically, that's the way radians are written, is as improper fractions when we use them for answers. So these 4, kind of challenging because of the large numbers, but really, really good in getting us to think about how we have to transfer that knowledge that 360 degrees is really 2 pi, and that radians are going to work with fractions. They always do. So lots of good math happens when you start talking about making perfect math, making elegant math, and that's what we're doing. In applications, it's sometimes necessary to connect angular speed, which is measured in units like revolutions per minute, to linear speed, measured in units like miles per hour. And most of this has to do with things like, why do you have to get your tires rotated? You know, there's 4 of them on there, they're all the same. Why on earth would you want to rotate them? Because we tend to travel the exact same place every day. You know, we go to work, we go back home. We go to work, we go back home. And every time that you take a turn, there are 2 wheels that get a little time off, while the other 2 have to travel a little bit farther. And that's why we have to rotate the tires. If they get used more on those turns, then they're going to wear more. So angular speed and linear speed, connecting those 2 things up. The other place is going to be anywhere that you have gears. So anybody that works in any place where you have machinery and you're using gears, it's another important application. This means we need to connect the 2 by one of the arc length formulas, or by using conversion factors that equate 1 radian of angular measure to 1 radius of arc length. This brings us back to unit analysis, also known again as dimensional analysis in your science classes. It has to do with the labels. So if we can just keep focused on getting the labels we want, then we'll be okay. So Albert Juarez's truck has wheels that are 36 inches in diameter. If the wheels are rotating at 630 RPMs, revolutions per minute, find the truck's speed in miles per hour. Whew! Where do we start? Well, they gave us some information. And there's one piece of information here that was just truly solid. There's no more thinking to do about it. And that is 630 revolutions in 1 minute. Now I know somehow I have to connect that to the circumference of these wheels. Somehow. So I start thinking, okay, well, circumference is 2 pi r, or 2 radiuses make up a diameter, so it's also pi d, which would be 36 pi. Now, obviously, it's going to be 36 pi inches. That's usually where students have a little trouble. So here's what I want you to do. I want you to look ahead and say, what is my answer supposed to be? My answer is supposed to be miles per hour. Now, I look at what I have so far, and I realize, well, minutes, that can get me to hours. I can work with that. I can get that to be hours. But this revolution, that's nowhere in my answer. So what do I know about a revolution that I could use to get rid of revolutions? The circumference. The circumference is 1 revolution. So if I put 1 revolution down here, now revolutions are on the top and the bottom, and they're going to cancel. And I already found out that it's 36 pi inches by figuring out that circumference. So revolutions is gone, and now I almost hate to cancel these out this early in the problem, but I need everybody to see inches per minute. And you realize, well, I could certainly work those out to be miles per hour using conversions. So I'll work with the minutes first. Minutes on the bottom means I need minutes on the top, which is good because my answer needs hours on the bottom. And I know there are 60 minutes in 1 hour. So now minutes will be canceled. And I at least have one of the 2 labels right. The other one is inches, so I have to work with that one. And I know there are 12 inches in 1 foot, so that's helpful. That's getting me closer. Feet are definitely bigger units than inches are. And then, I'll have to move this out because I write so big. Then I try to remember, oh, there's something I know about feet in a mile. Anybody brave enough to unmute and tell me if they remember that number?
5,280.
Excellent. I always say that one, and then people are laughing because I'm a math geek in the classroom. It's like, wow, you totally know that. Yeah, we should know that one. We've had to use that conversion before. And again, that will give us our miles per hour label that we need. Put that back on so the people that aren't necessarily here today are going to be able to see what we have. So, feet, gone. Only label we have on the top, miles. Only label we have on the bottom, hours. That's exactly what we need. Now, we have to take top times top times top times top times top and divide it by bottom times bottom times bottom times bottom times bottom. And let me tell you what happens every year on this test. People forget about this pi. They're so focused on getting the numbers that they forget that there's a pi up there to punch in. So don't miss the pi when you go to punch this one in. And typically, you won't see me write intermediate steps where we had to do rounding. But I want to make sure that you're punching this in correctly at least halfway through. So if you punch in 36 or 630 times 36 pi times 60 times 1, should be getting 427,000. Oh, I missed a number. There we go, that's better. 4,275,079.286 divided by 12 times 5,280 times 1 times 1 times 1. And that should come out to approximately 67.473 miles per hour. A lot of numbers to keep track of, so just be careful, go slow when you're punching that in. It's definitely another problem where in the tortoise and the hare race, be the tortoise, because like I said, people get so upset with themselves after the test when they realize they forgot to punch the pi in. They had everything else in there, but not the pi. Please unmute and let me know if you still need time for punching in. All right. Big topic here. There are actually two different kinds of miles. We've got a nautical mile, and that's shortened to NAUTMI, is the length of 1 minute of arc along Earth's equator. Obviously, many, many thousands of years ago, they were getting on the ocean trying to figure out how to get from one place to the other, and they were using the North Star, but they were hopeful that they could do something, like miles, so that people could understand how far they had to go, a distance. So central angle AOB down here of the Earth measures 1/60th of a degree, because it was 1 minute of the arc along the Earth's equator. And that 1/60th is considered a nautical mile. 1/60th of a degree, 1 nautical mile. So, we have some information underneath this that we don't normally have to pay attention to. But what it does is it informs us about some measurements that we need for these problems. Although Earth is not a perfect sphere, because it's not, its diameter is on average 7,912.18 statute miles. A nautical mile is 1 minute of Earth's circumference at the equator. Well, if I'm going to use this to find those distances, I'm going to have to figure out what is the radius of Earth. So we would have to take, oh, Owen, can you unmute for us, please? Or mute for us, I should say. We can hear everything right now. So 7,912.18 divided by 2, 3,956.09 miles. So that's going to be the radius of Earth. Right there. The arc length formula allows us to convert between nautical miles and statute miles. Those are the normal ones, you know, when we drive and say Big Lake is 13 miles from Elk River. Come on, there we go. Those are the land miles. So the land miles of 5,280 feet. So like I said, kind of weird how miles are not the same, but they're not. So that means if we want to understand how far two things are away from each other out on the ocean, we have to be able to go between nautical miles and statute miles. So we have to be able to transfer those over. Now, the key to this is that nautical mile is 1 minute of Earth's circumference at the equator. So, I'm going to move this down. Need a little space here. I look at those distance conversions and I think, I don't like that. I don't like that at all. Look at that. They went to the hundredths position. I want to know just exactly what the conversion really should be, the elegant conversion for this. So I focus on the fact that those nautical miles are 1 minute. And I realize that's 1/60th of a degree. But if I'm going to have any of this exact, I should change that into radians. So I should multiply that by pi radians over 180 degrees. So to get the exact conversion, top times top, pi. Bottom times bottom would be the 60 times 180, and that is 10,800. So that would be what we would use for an exact conversion. So then I think, all right, well, if that's going to be a nautical mile, I need to know what the arc length is. So my arc length is the radius of Earth, which we just wrote down on the previous page, 3,956. $3956.09 times the angle in radians, which is going to be pi over 10,800. Now, let's go ahead and punch that one in. 3956.09 times pi and divide it by 10,800. And we get so 1 nautical mile is equal to 1.150779933 statute miles. And they've lost a lot by moving that into the hundredths position. and rounding it. Likewise, they lose something on the other conversion. So what I want to show you here, because we already know all we're going to do is turn this upside down. If we take 3956.09 times pi, divide that by our 10,800, we had our first conversion. Now, to go backwards, we already know this. You know, degrees to radians, radians to degrees, you just turn the fraction upside down. Well, we have a button on our calculator that does that for us automatically, and that's the inverse button. It's just underneath the math key, x to the negative 1. So if we hit answer to the negative 1, now it flipped that for us. It made it its reciprocal, because when you raise something to the negative 1 power, you get the reciprocal. And likewise, that's a little upsetting that they decided to round to 2 decimal places for that one. Not exactly exact. So, not as elegant as it could be, but let's see how good it is. Megan McCarty, a pilot for Western Airlines, frequently pilots flights from Boston to San Francisco, a distance of 2,698 stat miles. Captain McCarty's calculations of flight time are based on nautical miles. How many nautical miles is it from Boston to San Francisco? So I want the stat miles to disappear. Which means I want the conversion for how many nautical miles there are. So if I want nautical miles per statute mile, I'm going to need my, and I don't want to use that one this time, 0.8689758.754. I have to grab my paper. There's no way I'll remember all those decimals when I write them down here. Now the good news is I still have that on my graphing calculator back there. So all I have to do is take it times 2,698. So 2,344.497 to 3 decimal places. And that, of course, will be in nautical miles. Now, what I find interesting is how much would they be off because they just used 2 decimal places. So let's go back. And say instead of using 0.8689758754, let's just use their 0.87. And see what we get. So that's going to give us 2347.26. Nautical miles. And make that 4 a little bit more readable. We realize it is going to be off because they didn't use the entire conversion with radians in there. But most sailors would say, on the ocean, you can see very, very far. And so if we can just get an idea of what we should be looking for in terms of miles, then we'll be okay. Mathematicians wouldn't say that. We would say, well, that's not the elegant way to do that. But they're saying close enough is close enough, and really, if you're talking about whether or not it's airlines or ships, that's probably true. They're going to be able to see it anyway by the time they get there. I mean, that's the reason that they have people up at the top of the ship saying, land ho! That's why they do those things. So that actually covers the last piece of what we needed to do, which was working with the word problems that involve everything that we're doing with trig. Now, this is definitely not everything, but it uses what we already know how to do. So, what you can do is definitely finish off the book assignment now. So yesterday you could finish up the worksheet from 13.2. Now you can definitely finish up the book assignment. So I'll expect that to be turned in tomorrow. And then tomorrow, no lesson. You won't have to watch a daily lesson video. We did get through everything we needed to from 4.1. So you will just work on the other worksheet. So that one's labeled 4.1 Day 2 in the black folder. And that's everything from section 4.1. So have a great day, everybody.